The modern world is filled with a lot of things and a lot of technology, valued at hundreds of millions of dollars, used for very specific purposes, which most of the world has no knowledge about. Some of these technologies keep people and even entire countries on the map. That's the case with the Maven smart system, developed by Palantir, one of the most expensive algorithms in the world, used by some United States intelligence agencies to integrate, process, filter, and visualize large volumes of data from phone communications, intelligence reports, military satellites, drones, among other sources, to assist commanders, agents, and military personnel on the ground in the decision-making process for national security situations. Perhaps above it, we can find Google's search and ranking algorithm, which is certainly one of the most important and most used algorithms in the world, which is designed to rank hundreds of billions of web pages and other digital content and present the most relevant and useful results to you, right on the first page in a fraction of a second. The price of the algorithm is in the hundreds of billions of dollars, but it is considered by many to be priceless. That's because the algorithm has been continuously improved for over 20 years. And how much has been spent over that time is information that only Google knows. But there are many other things in this world that have astronomical prices, especially when it comes to materials and substances. Rhodium, $70,000 to $150,000 per kilogram. Gold, silver, and platinum are the most popular precious metals in the world. However, the most valuable one is almost unknown. Discovered by William Hyde Wollaston in 1804, rhodium, one of the world's priciest metals, is part of the platinum family. It is a precious metal, extremely rare, silvery white, ductile and brittle. At room temperature, rhodium is in a solid state, and it is extracted as a byproduct from platinum and nickel mines, mainly in South Africa, Russia, and parts of America. To give you an idea of how rare it is, the production of this material as a byproduct of other mining activities is only 7 to 8 tons per year worldwide. One of the most well-known applications of rhodium is in vehicle catalytic converters, which are parts of the car's exhaust system that serve to neutralize toxic substances produced by combustion in the engine, such as hydrocarbons, carbon monoxide, and nitrogen oxides, and transform them into harmless gases such as water, carbon dioxide, and nitrogen. Rhodium is used in aircraft spark plugs, electrical connectors, jewelry, and decorative items. Plutonium, 4 to 5.6 million per kilogram. At room temperature, plutonium is in a solid state. It is a radioactive chemical element, brittle, very dense, and silver white in color, extremely rare in nature, and it tarnishes when exposed to air. Being radioactive means that its nucleus is unstable. And to stabilize itself, it is constantly emitting alpha, beta, and gamma particles, which are harmful to human health. They can cause cancer, rapid aging, genetic mutations, and significantly reduce lifespan, among other effects, especially when ingested or inhaled. It powers nuclear reactors, while its isotope plutonium-239 is used to make nuclear weapons. Especially the Fat Man, the largest nuclear fusion bomb used against humans in Nagasaki, Japan. Containing 6.4 kilograms of plutonium, the Fat Man unleashed 21 kilotons of explosive force, equivalent to the explosion of 21,000 tons of trinitrotoluene, or in other words, trinitrotoluene, which resulted in the instant death of 40,000 people. Osmium-187, 10 million per kilo. With atomic number 76, osmium is the rarest element in the Earth's crust and also the densest element on the periodic table. At room temperature, osmium is in a solid state and is a byproduct of platinum. However, its isotope osmium-187, which is not radioactive, is used together with rhenium-187 for dating rocks and meteorites in the method called rhenium-osmium dating. This method is used to determine the age of ancient rocks and meteorites that are billions of years old. Osmium-187 is one of the elements that helped scientists understand the origin of our solar system, because it's found in ancient meteorites dating back over 4.5 billion years. Osmium-187 is also used as a metal alloy enhancer, making them ultra-resistant metal alloys, especially when combined with platinum and iridium, for aerospace and medical applications. Tritium, 30 million per liter. Tritium is found in a gaseous state, and you've probably already had the chance to look at and even hold something containing tritium. It's used in luminous signs such as emergency exits in theaters, illuminated signs, billboards, and gun sites. It emits a fluorescent green glow that can last up to 25 years without needing any kind of external power. Tritium is a radioactive isotope of hydrogen that is not naturally found on the Earth's surface. It is found in outer space and around the Sun. However, its production, which is extremely expensive and in tiny quantities, is done in nuclear reactors by bombarding lithium-6 with neutrons. Another use of tritium combined with the deuterium is to be part of weapons of mass destruction, such as atomic bombs. The main function of tritium is to increase the yield of nuclear fission and thermonuclear weapons, boosting the destructive potential of the bomb, as very well illustrated in the Teller-Ulam design of a modern thermonuclear bomb, in which the presence of a container storing tritium and deuterium gas is illustrated as part of one of the several components that make up the bomb. Yeremeyevite, 50 million per kilo. Although humanity may never be able to gather a kilo of this gem in one place, it is considered one of the rarest, most valuable, and most expensive gems in the world. Yeremeyevite is an aluminum borate mineral with variable fluoride and hydroxide ions. It is a rare, transparent mineral, blue, colorless, or pale yellow in color, that belongs to the borate class. Yeremeyevite does not have widespread applications in modern science, industry, technology, or even in jewelry. Due to its rarity, mineral and gemstone collectors highly seek it. It was discovered in 1883 in small, isolated crystals, in loose granite debris on Mount Sokhtui in Siberia, a region belonging to Russia. This mineral was also found in large, faceted crystals in Namibia in the 1970s. It was named in honor of Pavel Vladimirovich Yeremeyev, a Russian mineralogist, engineer, and professor who collected the first samples. Gold 198, from 50 million to 100 million per kilo. Unlike common gold, gold 198 is a radioactive isotope made in nuclear reactors by irradiating gold 197. It is a beta radiation emitter and has a relatively short lifespan, about 5 days. After that, it decays into mercury 198. Its high cost is due to the fact that it is produced exclusively in nuclear reactors and in very small quantities. To make it worse, it decays after just 5 days. Gold 198 is widely used in brachytherapy, a type of internal radiotherapy. Small radioactive seeds of gold 198 are implanted inside the patient's tumor. The beta radiation it emits, which penetrates up to 4 millimeters into tissues, destroys cancer cells locally without irradiating the entire body. Since gold 198 has a short half-life, only 2.7 days, it decays quickly, reducing risks after treatment. Gold 198 is also used to trace leaks in industrial pipelines and nuclear reactor pipes, and it can also be used in a salted bomb. A nuclear weapon designed to function as a radiological weapon, producing greater amounts of radioactive fallout after detonation than regular nuclear weapons. This fallout can make a large area uninhabitable for decades, just like in the exclusion zone around the Chernobyl reactor. Red or blue diamonds, 300 million per kilo. Diamond is the hardest naturally occurring material known. And this hardness means it can't be scratched by any other mineral or substance except by other diamonds. When it's rough, that is, before going through the cutting process, its price can be up to 10 times lower. They are still some of the world's most valuable and costly gemstones. However, those with rare colors such as red, blue, or intense pink, which have colors caused by impurities or defects in the crystal structure of the stone, are the rarest, most valuable, and consequently, the most expensive in the world. Blue diamonds, for example, represent less than 0.1% of the diamonds mined in the world. The first were extracted in India in the 1400s. However, over the past century, blue diamonds have also been found sporadically at the Cullinan mine in South Africa, and they continue to produce rare stones to this day. Perhaps the most famous blue diamond in the world, the Hope Diamond, is a remarkable fancy deep grayish blue diamond weighing 45.2 carats. Valued at over $200 million, the history of the diamond dates back to the 17th century, when it was first acquired in India by the French gemstone merchant Jean-Baptiste Tavernier. Initially weighing 112 carats, the stone was eventually cut into a 69-carat gem and became part of the French crown jewels. In recent times, the De Beers blue diamond reached a record sale of $57.5 million. At Sotheby's in April 2022, it became the most expensive blue diamond ever sold at auction, weighing an impressive 15.10 carats. However, the Pink Star diamond is the most expensive diamond ever sold in the world. With 59.60 carats, it was sold for an incredible $71.2 million at an auction in 2017. The multinational De Beers mined the Pink Star in South Africa in 1999. The diamond weighed 132.5 carats in its rough form, and it took 20 months to cut and shape the diamond. Californium 252 Cortesi 27 billion per kilo. Californium 252 does not exist naturally on Earth. It is artificially created in nuclear reactors by bombarding curium-249 with neutrons. It is an extremely radioactive isotope of californium, extremely rare, valuable, extremely harmful to human health, and difficult to obtain. Normally, it's a solid silver-colored metal. To give you an idea of how rare and difficult its production is, it is mainly produced in only 2 places in the world. At the Oak Ridge National Laboratory in the United States, which is the largest producer in the world, and at the Dimitrovgrad Research Institute in Russia, the only other significant producer in the world. Producing just 0.25 grams of this material takes 6 months to a year because the process is so complex. Only international organizations can buy it. With a half-life of 56.4 years, it is a strong neutron emitter, making it extremely radioactive and harmful to human health. 1 milligram of this material spontaneously emits 170 million neutrons per minute. Californium 252 is used in the analysis of the surface of other planets through space probes. It is used to find hydrocarbon-rich layers in oil wells. It is used as a neutron source to initiate reactions in nuclear reactors. including those in nuclear submarines, and it is also used to detect hidden materials, such as explosives and drugs. Francium, 1 trillion per kilogram. A francium here and another there, but none anywhere. Discovered in 1939 by Marguerite Perret, francium is a highly radioactive chemical element with atomic number 87. Its electronegativity is the lowest known, and it is the second least abundant element in nature, with the first being astatine. It is so rare, but so rare, that it is estimated that only 30 grams of it are present on planet Earth at any given time as a byproduct of uranium decay. Incredibly enough, francium has no practical application, whether commercial, industrial, or medicinal, serving solely and exclusively for scientific research. This is due to the fact that its half-life is only 22 minutes, making it impossible to accumulate, store, or sell. It is produced only in small amounts in nuclear reactors and particle accelerators. Scientists create francium by bombarding gold-197 with oxygen-18 ions. The catastrophic price reflects the astronomical costs of isolation in controlled environments, inside vacuum chambers, lead, or magnetic fields, to avoid chemical interactions and radiation scattering. Therefore, it is used for scientific purposes such as studies in quantum physics and biology. The amazing thing is that since the discovery of francium, we still don't know exactly what it looks like, because it has never been possible to obtain a stable enough metallic sample for it to actually be observed. Scientists study francium using non-contact techniques such as laser spectroscopy. Antimatter, 62.5 trillion per gram. Antimatter is one of the most fascinating concepts in modern physics. It is also the most powerful substance in the known universe, the most dangerous that humans are aware of, and the most expensive substance in the entire universe. It is believed to be found at the center of galaxies, in pulsars, and in black holes. However, humans have been able to produce it artificially here on Earth. In particle physics and quantum chemistry, antimatter is the opposite counterpart of ordinary matter. It is composed of particles called antiparticles, which have the same mass but opposite electric charge compared to normal particles. While in ordinary matter electrons have a negative charge, in antimatter they are called positrons and have a positive charge. Neutrons in ordinary matter have a neutral charge. In antimatter they're called antineutrons and also have a neutral charge. Whenever matter and antimatter meet, both are instantly annihilated, releasing colossal amounts of energy. Antimatter is produced at the Large Hadron Collider, at Conseil Européen pour la Recherche Nucléaire, which is in Switzerland, and also at Fermilab in the United States. These laboratories accelerate particles to speeds close to the speed of light and make them collide, generating small amounts of antiparticles. The big problem with antimatter is that it can't touch matter. The mere presence of air already causes them to annihilate instantly with 100% energy release. To store them, Conseil Européen pour la Recherche Nucléaire use magnetic traps, called pinning traps, to suspend the antiparticles in a vacuum without contact with any surface. Besides that, the temperature needs to be extremely low, minus 270.50 degrees Celsius, to keep the particles stable. Conseil Européen pour la Recherche Nucléaire has already managed to store 300 atoms of antihydrogen for 17 minutes, an impressive record. However, since the 1990s, Conseil Européen pour la Recherche Nucléaire has produced a total of about 10 nanograms of antimatter. Assuming that Conseil Européen pour la Recherche Nucléaire produces 10 nanograms of antimatter per year, considering that 1 gram is made up of a billion nanograms. Conseil Européen pour la Recherche Nucléaire would take approximately 100 million years to produce a single gram of antimatter. That's an eternity. Besides the high energy consumption of 120 megawatts when it's operating. One of the most prominent uses for antimatter would be to make weapons. A single gram of antimatter can generate approximately 43 megatons of trinitrotoluene in destructive power. Just to remind you, the Tsar Bomba, the largest atomic bomb made by man, released 58 megatons. Another use of antimatter is in space propulsion. Antimatter-powered spacecraft could reach 10% of the speed of light, making interplanetary and interstellar travel feasible. National Aeronautics and Space Administration has already studied matter-antimatter fusion engines, which would require only 10 milligrams of antimatter to propel a spacecraft to Mars in 45 days. It is also an excellent energy source, practically infinite, where just a few kilograms could provide power for entire continents. If humanity managed to produce 1 kilogram of antimatter, it would be worth more than the gross domestic product of all the countries in the world combined.